Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Bada bin Fikir bin Muhammad Kumar.
I'm Muhammad Arif bin Azam.
I'm Muhammad Haziq bin Saharudin.
Okay, today my team from Group 9 want to present to you about AC power analysis about power factor correction.
Okay, for the task 1 of this assignment, a network consists of 3 loads are connected at 3 different nodes as shown in figure 1, and the 3 distribution lines are connected between the main supply and loads. Voltage required by load 3 is 240 angle 12 VRMS, and the details of the network are given in table 1. It is the table 1, information is given for us. This is the circuit diagram. The impedance for each load and the equivalent impedance. We start with load 3. Okay, for the first step, we must find the real power of load 3. The real power is sum of apparent power plus reactive power. The apparent power and reactive power is given in the table. You can see it, 200 kV and 12 kVAR. So we just plus it for get the real power at load 3. After that, we must find the impedance at load 3 by divide voltage at load 3 is given in the question, 240 angle 12. We modulus the voltage and square it and divide by real power at load 3 and conjugate, we will get the impedance at Z3. After that, we must find the impedance at load 3 by adding the impedance load 4 with the impedance 3. After that, we must find the current at load 3 for us for find the voltage at load 2. For find the current at load 3, we just divide the voltage load 3 modulus and square divide by impedance load 3 and we will get the current at load 3. Now we can get the voltage at load 3 by multiply current load 3 with the impedance load 3. The voltage load 2 is important for us for find the information at load 2. I will explain detail in load 2. Load 2. Power factor of load 2 is given in this table. We will see 0.85 leading. So we can find the angle with inverse the cos and multiply with the power factor. It is because the formula of power factor is cos theta, and we will get the angle 31.79. After that, we must find the real power of load 2. For find the real power of load 2, we just divide the apparent power load 2 by the power factor. The apparent power of load 2 is given in the table, 15 kV. So we divide the 15 kV with the power factor 0.85 and we will get the real power at load 2, 17.85 kVA. So we must write the answer like this: 7.85K angle negative 31.79 VA. The negative sign because the system of the load 2 is leading. so it negative. After that, we must find the impedance 2 by divide the voltage at load 2 that we get at the load 3 240.018 angle 12. We just modulus it and square and divide by the real power at load 2 and conjugate it, and we will get the impedance 2. After that, we must parallel the Z2 impedance 2 with the impedance load 3 that we get in the previous slide. This is the impedance load 3 that we get in the load 3. So after we parallel, we can get the circuit like this. So the next step, we must find the impedance load 2 by adding the Z parallel with impedance 5. Z parallel, impedance parallel must add with impedance 5. So we will get the impedance load 2. After that, we must find the current of load 2 by divide the voltage load 2 with the impedance parallel. And it is the current load 2. After that, we must find the voltage load 1 by multiply the current load 2 by impedance load 2. The voltage load 1 must find because we will use it in the to find the information of load 1. I will explain more in load 1. Okay, this is load 1. The power factor of load 1 is given. We can see 0.92 lagging. So for us to find the angle of this load, we just inverse the cos and multiply by 0.92 and we will get the angle 23.07. After that, we might find the real power of load 1 by divide the apparent power with the power factor. Apparent power of load 1 is given 10 kilovolt. So we divide the 10 kilovolt with the power factor to get the real power of load 1. After that, we must write the answer like this. The angle of this real power load 1 is positive because the system is lagging. We can see it in the load 1. The system is lagging. After that, we can find the impedance at load 1 by divide the modulus of voltage load 1 square divide by real power at load 1 and conjugate it. The voltage load 1 we get in the previous slide. You can see it 288.49 angle 25.38. So when we make the operation, we can get the answer of impedance 1. After that, we must parallel the impedance load 2 with the Z1. After we parallel it, we can get the circuit like this, right, of the screen. After that, we just add the impedance parallel to with impedance 6 to get Z total, and Z total is 2.42 angle 34.89. Okay, I will pass the presentation to my partner Haziq.
Next, we will calculate the current flow for each node and the total current. For the total current value, the formula will be voltage at load 1 divided with resistance ZP2. We will get the total current value is 167.75 with an angle of 5.93 degree ampere. And for the current at load 3, we have already made the calculation from the first part of video, which will get the value is 83.63 with angle of negative 24.82 degree ampere. Moving on to the next step, to find the current at load 2. The formula will be the same as voltage at load 2 divided with the resistance at Z2, and we will get the answer is 73.54 with angle of 43.79 degree ampere. With the current at load 1, the step will be the same as the current at load 2, which is the voltage at load 1 divided with the resistance at Z1. We get the value is 37.71 with an angle of 2.31 degree ampere. Next, to determine the main power supply. From the previous calculation, we already have the current total value, which 167.75 with an angle of 5.93 degree ampere. By using the Ohm's law, V equal to IR, or in this case is Vs equal to current total multiplied with the Z total, we will get the voltage supply value equal to 405.9066 with angle of 40.82 degree voltage as our main power supply. Moving on to the next step, to find the real power and reactive power losses at the transmission line. So we have 3 transmission lines from line 1 to 2, line 2 to 3, and line 3 to 4. For the line 1 till 2, to calculate the power, the real power value is by using the formula I square R, which is I total squared multiplied with R1. We will get the value of 10.13 kilowatts for the real power, and for the reactive power, by using the same formula I total square multiplies with imaginary value, we will get the value of 22.79 kilowatt. Thus, we can have the apparent power for the line 1 till 2, which is 24.9399 kilo with an angle of 66.04 degree voltage ampere. Moving on to the next line, for line 2 and 3, the step will be the same. For the power at line 2 to 3, with the formula of current at load 2 square multiplies with resistance, we will get the value of 4.55965 kilowatt. Next, for the reactive power losses at line 2-3, the formula will be the same, which is the I current at load 2 square multiplies with the X imaginary. We will get the 9.11930 kilo voltage ampere reactive. Then we will get the apparent value for the line 2 and 3, which is 10.1956 kilo with an angle of 63.43 voltage ampere. Moving on to the next line for line 3 and 4. For the power losses at line 3 and 4, with the formula of current at load 3 square multiplies with resistance at load 3, we will get the value is 1.25892 kilowatt. For the reactive power at load 3 at line 3 and 4, using the current at load 3 square multiplies with the imaginary value at load 3, we get the value is 3.14729 kilovoltage ampere reactive. Here we can get the apparent power value for the line 3 and 4, which is the value is 3389.736 with an angle of 68.19 voltage ampere. So for the next step is to calculate the total apparent power, real power and reactive power in the system. From previous calculation, we already have the power, the real power calculation, the reactive power calculation. And here we can calculate the total apparent power by using the formula of the total voltage supply multiplies with the load total, which we will get the value is 55,844.96 plus 38,943.498 kilo voltage ampere. As the angle here is 34.89, which is the positive value, so we can have the cos theta, which the theta is a positive value, is equal to 0.820. In terms of power factor, it is a lagging condition. Therefore, the system is in lagging condition because of the positive value of angle. Here we can draw the power triangle, which we can put the S, the apparent power value, the reactive power value, and the real power value, and the theta, the angle for our system is 34.89 degree. For the task 2, based on the network that we designed in the task 1, design the power factor correction system that helps to improve the system power factor to 0.98 in the lagging condition. With the cos theta, the power factor given is 0.98 and our new reactive value is 11.48. By using the formula tangent theta equal to reactive nu over with power, we get the Q nu, the reactive nu value is 11,341.49 kilowatt. So for the QC, to find the QC, which is the Q load, reactive load minus with reactive nu, we will get the value is 27,602.0115 voltage ampere reactive. From this value, we can find the capacitor value that we need by using the formula of QC is equal to voltage supply square divided with XC. So we can get the value of C here, which is 5.3326 times 0 power of negative 4, or in other words, the capacitor value is 0.533 millifarad. So this is the value that our capacitor need to achieve the power factor of 0.98 in the lagging condition. So for the next video, for the next part, I will pass it to my friend Muhammad Arif. Thank you.
Okay, for the simulation on task 3, we use multisim to perform AC analysis that we designed in task 1 and evaluate whether the value on task 2 are correct. So this is the circuit diagram that we mentioned earlier. All values are stated on each component. Okay, this is the result from what we got on single frequency analysis at 50 Hz frequency. The value shown is the current reading that are measured on each load from R1 until R6. The value are recorded by polar form, which allow us to see the magnitude and phase angle. Okay, this is the result of power factor when a no capacitor is placed in the circuit, which is the circuit has no switch. As we can see, the power factor of the circuit is 0.1659, which is equivalent to 0.82, and on the top of the wattmeter shows the real power value. Okay, next, when the circuit is placed, the capacitor of value of 0.533 millifarad, which means we apply power factor correction on the circuit, and the power factor increase to 0.98, that is nearly to 1. So that means the higher the power factor that we get, or the power factor is nearly to 1, so the more the efficiency, power efficiency towards the circuit. Okay, this shows the apparent power value for the power factor of 0.82 from the initial circuit. The formula to get the value is written as in the table in the single frequency AC analysis on the variable table. On the figure 6, same goes to the reactive power value. The formula is still the same as the apparent power value, but we just change the value from polar form to the rectangular form. As we can see, we can know the real and imaginary numbers. So this is the table. These are all the values of each individual real power value. When switch is off, that means the power factor is still 0.82, the initial one. Is the value for starting across inductance 4, 5, 6, and resistance of R1, R4, R5, R6. Okay, this is the comparison table for voltage and current that we just calculated earlier in task 1. We compare both calculation and simulation all together. However, there are some differences value obtained, but that will not affect significant changes to the data analysis carried on in this assignment. We also include the differences of apparent power, real power, and reactive power according to simulation and calculation. Data that we calculated are recorded in the table as follows. So there are no significant changes between both table, and it's okay to continue to this assignment. Okay, that's all from us. Thank you.